Hello everyone, I'm Xinyuan Li from Computer Network and Information Center of Chinese Academy of Science, and the title of my presentation is Large-Scale Simulations of Peridynamics on Sunway TaihuLight Supercomputer. Here is the outline of my presentation. First, I will give some introductions to the models, platform, and challenges as the background. Second, optimizations from three aspects are introduced. Then I will give the result of performance evaluation to show the performance of our application when facing small-scale and large-scale simulations. Finally, conclusions and future work will be claimed. First, I will give some introductions to PD models, Sunway TaihuLight, and the challenges to implement PD simulation applications on Sunway TaihuLight. Peridynamics is a non-local mechanics theory proposed by Stewart Stirling in 2000. The models are built based on the idea of non-local behaviors and describe the mechanical behaviors of solids by solving special integral equations. Because of the superiority on simulating the discontinuous problems in recent years, the PD methods have been widely used in material science, human health, electromechanics, and disaster prediction, and so on. The simulation processes update the state of points by solving the mechanical equilibrium equation. When looking into the equation, we can find that the integral or summation is used to calculate the internal force of a point by summing the interactions between other points in the spherical area Hx, where x is the center point and delta is the radius. In order to describe the crack initiation, propagation until the failure, the concept of local damage of the material point is introduced. Here D is the local damage, and phi denotes the bond damage flag. From the equation, we can find that the main advantage of PD methods is that PD methods can avoid the cutting-edge singularity of traditional numerical methods using special differential equations. So PD methods have the superiority on simulating the discontinuous problems. And the main disadvantage of PD methods is that PD simulations based on the integral equations are usually much more computationally intensive than the traditional methods using differential equations. Because PD simulations are computationally intensive, it is necessary to implement PD simulation application on supercomputers. Sunway TaihuLight as one of the most fastest heterogeneous medical supercomputer is suitable for PD applications. Sunway TaihuLight consists of more than 40,000 SW26010 processors. A processor consists of 4 crew groups, each including 1 management processing element and 64 computing processor elements. DMA is used by CPs to exchange data with MPE in the same core group. There are 2 instruction pipelines in each CPE, which enables overlapping between memory access instructions and computation instructions. We summarize 4 challenges to implement PD applications on Sunway TaihuLight. The first is that DMA requires the data block more than 128 bytes to make data transaction between CPs and MPE efficient, so the data organization should be adjusted. Second, bandwidth between CP and MP is relatively low compared to the compute ability, which will make the simulation become memory-bound. Third, data dependencies and high latency instructions in bound-based part affect the throughput of instruction pipelines. Finally is that the cost of communication between processes may be obvious when facing large-scale simulations. Now, I will introduce the optimizations we do to solve the challenges from 3 aspects. There are 2 optimization approaches for memory access. One is the data grouping for DMA and the other is the SPM-based cache strategy. To make the DMA efficient, The data block used for DMA should be larger than 128 bytes. We need to pack the data into a layout that is suitable for DMA transaction. Each point consists of 6 items, 3 3-dimensional vector items, and 3 1-dimensional scalar items. Based on the usage of data in the algorithms, we combine a vector item and a scalar item to a 32-byte data block, and then combine 4 32-byte data blocks of 4 points into a 128-byte data block, which is used as the basic unit of DMA. To make vectorization efficient, the data in a group are stored in struct of array layout. Each CPE has a 64 KB SPM. To reduce the amount of data fetched from main memory, the SPM-based cache strategy is proposed. In the PD simulation, during the calculation between bounds, each point is accessed multiple times by CPEs. Performance can be improved if CPEs can read most of the required data from the SPM. When the data of a group is needed by a CPE, the CPE will first get the index and the flag of group. Next, CPE will compare the flag of group and the flag in the corresponding position in the cache. If 2 flags match, it means the data is already in the cache. Otherwise, CPE will fetch the data with DMA. Because of the locality, the CPE will fetch the data of next group at the same time, which can play the role of data prefetch and improve the DMA efficiency. After reducing the cost of memory access, we use vectorization and further optimizations to improve the computation efficiency. When we vectorize the kernel, the basic compute unit is changed from a point to a group. The interaction of all 16 bonds between the two groups are calculated, but some bonds are invalid because points in two groups are not necessarily neighbors. Red lines in the figure represent the invalid bonds. The vectorized comparison instruction is used to compare the length of bonds to the integral radius and get a set of 16 flags, where 0 means the bond is invalid. By multiplying the flags to the interaction results, the invalid results will be set to 0. After vectorizing the kernel, to fully utilize the instruction pipelines, we need to optimize the scheduling manually. The throughput can be improved from 3 aspects. The first is to reduce the data dependencies between instructions by inserting independent instructions between 2 dependent instructions. To reduce the dependencies, unrolling the loop is a feasible way because the calculations of the bound is independent except the reduction step. Moreover, reordering the instruction sequence can further reduce the dependencies. Second, we can overlap the memory access instructions with floating point instructions because the amount of floating point instructions are much more than the memory access instructions in the kernel. Finally, we can reduce the high latency instructions. One approach is refining the calculation algorithms. For example, replacing the division with multiplying the reciprocal of the divisor. The other is replacing the high latency instructions, including square root, division, inverse square root, with software improvement version. After optimizing the instruction scheduling, we vectorize the operations of bound damage flags for better performance. 16 damage flags of 16 bonds between two groups are stored as 16 bits in an integer. Before taking part in the calculation, the flags need to be decompressed and changed into double variables. When decompressing the flags with vectorization, we first broadcast the integer to 4 256-bit vectors and do AND operation with nth power of 2. Then compare the result to 0 with vectorized comparison instruction, and finally get the 16 double-type bond damage flags. When updating the bond damage flags, we first multiply the flags with double-type s power of 2 and do reduction of elements in 4 vectors. Finally, add the results to a magic number to change the type from double to long and extract the low 32-bit to get the compressed bond damage flags. When facing large-scale simulations, the communication cost will affect the performance. Overlapping strategies at 2 levels are proposed to reduce the cost of data transmission. The overlapping at process level can be divided into 2 parts. One is the overlapping between data packing on MP and data communication with MPI. When MP is packing data for a process, data for another process is transferred at the same time. Then, the other is overlapping between CPEs and MP. When MP is packing and receiving data, CPEs are computing with the data already in the process. After receiving all the data, CPEs finish the rest of calculations. At the CPE level, we design a double buffer strategy to enable overlapping between DMA and the calculations. In order to achieve the overlapping between calculation and DMA, besides the SPM-based cache on CPE, we set an additional buffer named DMA buffer to store DMA data for next calculation. Before starting the calculation, each CPE first finds the next group, which is data not in the SPM. Then the CPE fetches the missed data with DMA while calculating with owned data at the same time. The missed data will be fetched to DMA buffer at first and moved to the cache after the end of this round of calculation. Next, I will show the results of performance evaluation. We first evaluate the performance on a core group. Next, we compare our work to the popular PD simulation software Perdigm, and finally test the scalability of our application. All the cases are taken or generated from Perdigm, which is one of the most popular PD simulation software. The case we use simulates the infringement process of a cylinder. The table shows the parameters of the case. The left figure shows the cylinder at the start time, and the right shows the state of the cylinder at the end of the time. First, to evaluate the optimizations, we run 5 versions of our application on one core group of SW26010 processor with the example with 36,000 points. The SCR version denotes the serial version run on 1 MPE, and the power version denotes the parallel version with memory access and overlapping optimizations. The real version denotes the version optimized by instruction reordering based on the power version. The soft import version denotes the version optimized by software implement instructions based on the real version. And the bounce version denotes the version adopts all optimizations. From the result, we can observe a speed up of 181.4 times is achieved compared to the serial version run on MPE when run with example with 36,000 points. Next, I will show the breakdown of power version and bounce version. We can see that our optimizations on vectorization speed up the kernel about 3 times. As for the bond damage flags, the vectorizations of operations of bond damage flags in deletion part get a 1.9 speed up, while get a 3 speed up in first part. It is because in deletion part, both compression and decompression are needed, while only decompression is needed in first part, and speed up of compression is relatively low because of data dependencies. Here we show the performance results got by running our application with 4 examples on one core group. The cache hit ratio achieves more than 90% on all 4 examples. The best performance achieves 21% of the peak double position performance. To prove our work is efficient enough, we compare our application to the Perdigm run on the Intel Xeon E5-2680. To make the comparison fair, our experiment based on the similar energy consumption. So we compare our application run on one core group to the Perdigm run on an Intel Xeon E5-2680V3. The experiment setup is shown in table. We test the performance with 3 examples. From the results, we can observe that, compared to the Perdigm run on the Intel Xeon E5-2680V3 with 1 process and 1 CPU, our application on one core group can get a speed up of 60 and 6 times respectively. Here I will show the results of scalability evaluations. For the weak scaling test, the size of points assigned to each process stays constant, for example 36,000 points, and the number of processes is from 64 to 8,192. The results show that the parallel efficiency is almost ideal and indicate that our application can support large-scale simulations efficient. For the strong scaling test, we fixed the problem size to 148 million points and execute the example using different number of processes from 64 to 4096. The parallel efficiency is over 90% when the number of processes scales 64 times. The parallel efficiency decreases because of the cache misses happen at the early stage of the simulation. The smaller the problem size per process is, the higher the proportion of times it takes to read the data through DMA at the beginning is. Here I will give 2 conclusions of our work. The first is that experimental results show that the optimization techniques proposed in this paper greatly improved efficiency of the large-scale PD simulations and finally provide an efficient application on the Sunway TaihuLight. And the second is that the data transmission between the slave and the master and the weak ability of the compiler to optimize CMD calculation instructions are also common problems on other heterogeneous manifold platforms. So our work can offer insight into similar applications on other heterogeneous manifold platforms. As for the future work, we will first try to do large-scale PD simulations which solve real problems. Second, we would like to transplant the Perdigm to Sunway TaihuLight because Perdigm supports many solvers and models which can be useful to do PD simulations. Finally, we will implement an efficient PD simulation software on the GPU clusters, as the compute ability of GPU may give us chances to improve the performance of PD simulations. Thanks for your listening. I'm looking forward to your questions.